Hey,
Hey, how are you?
I'm good, thanks. Nice to finally meet you.
Yeah, it's very good. Sorry, my life was a little bit crazy in
No, it's good.
some
I mean,
time.
it's exciting. I've got lots of research and things happening. It's good to be busy.
Yeah, it's good, but I has a lot of work to do.
Yeah,
But
well,
of course,
I'm
thank you.
no, thank you. I've been experimenting with your library, and it's made me realize how little I know about just intonation and all the
Yeah,
mathematics I need to learn.
yeah, have a lot of my things. I like it, and OpenMusic can help you a lot with these things.
It's your library is amazing, and
Thank you very much.
I think it's like to I really want this to be just a video that people can who are interested in just intonation and
Yeah,
know your libraries there but don't really understand what all the
yeah,
functions do. It's fun, but it's there's so much to learn, and it's so I
yeah.
think even like a lot of the functions that you've got in your library, it was like another world for me. I've been kind of stuck with the with Harry Partch really, and I've been looking at microtonal composers like Ben Johnson who and
Yeah.
Mark Sabat as well,
Yeah.
his stuff.
Hmm. Yeah. Because that I work with I divide the library. So this is of Harry Potter work, and
Mm,
it's not its relation with other works. So yeah, I understand. It's very tricky sometimes. I will start to speak about the library.
yeah.
Yeah. Uh, the first thing I think that the library it's divided in four parts. Yes, then we have the just intonation utilities, and then we have the Harry Partch works and theories, the implementation of Harry Partch, then the implementation of one theory that is called Erwin Wilson. He's very well, I don't know, but in Brazil we not know him. I think he, but he worked with genes, the diagrams and figures in the genes of music. He did it, so he was very near to Partch. Then we have the Ben Johnson works, but just the work tuning system that he used in he was using in the string quarter number 2 and number 3. And then we have other functions that are some things that I just need and put here. Well, the main object for just intonation works, of course, is the ratio to mid-sense. Um, it works in a very simple way. Here, in the first inlet, we have the ratios, yeah. And then here in the second, we have the fundamental that are used to build this ration in or convert this ration in mid-sense. And here we have the mid-sense. It works with lists and ratios. This I find a very cool function in some Lisp works, not OM works, Lisp works, that tell us when the list that we have, it's a list or a list of lists. So it can make our work more easy. This we don't need to use the flat, and this is good. I think it's more it work
Yeah.
better.
What's can I
Uh,
ask what function that is?
yeah, it's I can show you. Maybe it's better.
Yeah.
I don't know the name because I I I just put it here, but it is this function.
Hmm.
Lisp of Lisp P is to this two. Yeah.
Yeah, I see.
So it's the train code of Reddit. I don't know him, but
Yeah.
it's
Oh,
a
I know.
very good code. Yeah.
That's great. Yeah, no, I will definitely
Yeah.
steal that.
Yeah, it's very good because I think some people don't know very well are starting to work with OM. So this kind of error, it's a very tricky to understand what is the error, I think. So to maybe make this more easily, I am working with more code between inside the blocks, yeah, the objects. But when we are working with the patches, it make the coding work more easy, I think. Yeah.
Yeah, I think that's one of the
So
things I really like about your library as well is the error messages are so clear about
yeah,
maybe why something's not working, or just the fun comments that you have written whenever you use a function.
yeah. Was one maybe on recommendation of my supervisor in my MA. He was very interested in my library too, but he uh, was concerned about the people of the graduation, yeah, undergraduation students. He was concerned about they, and he suggests me to work with a very simple way, yeah, make trick things, of course, but in simple ways. And these messages are maybe an attempt to work with or make the work more simple. Yeah. So then we have some, let me see what's the next object. Oh, the range reduced. Yeah. This object, it's the name, they reduce a range of pictures. So I am working in my compositional work with very big ratios. Yeah. So here we have one. You can see that it's very big ratios. Yeah. And of course, you need to put these nodes in some audible range. Yeah. So here it's very higher, all the nodes. So this object will do it. In the first inlet we have the nodes, the bit sets. The second inlet it's the more lowest node, yeah, the lowest.
Yeah.
And the third inlet we have the higher node. So it will put it all the nodes of the bit sets inside this range. So it's very simple. It works with here we have a list of lists, yeah,
Yeah.
and it work with just lists too, of course. You can see it here. Then it is maybe the people that will use this function must be some care, maybe, because if you are interested in do some symmetrical things and you do it before this object, yeah, before this object will destruct your symmetrical
Of
things.
course. Yes, because everything's being,
Bec
because you've got the that kind of symmetry comes from the ratios, which then have been
yeah,
totally because you've really destroyed those kind
yeah,
of relationships to bring it into
yeah,
an audible range. So you have to be very careful about where in the
yeah,
order of functions that you do this.
because it worked with a loop. So he will ask in the node 1 4 times. Oh, this node is higher than this and lowest than this. If yes, you okay, just let it. And but if not, decrease this sense. So it's
Yes,
he
I see.
will work. Yeah, the number of decrease the sense it's variable. He will decrease this note, the higher notes, by this note, the lowest note. So here we have 2,400. Yeah.
Mhm.
Then it will reduce all the notes by this number. If I put here, let me see here, I think. For example, here I have a change because it will work with 2,400. Yeah.
Yeah.
Okay. Yeah. Yeah. So the next is this object rt-octave. It does the same thing, but in the ratio environment maybe. So it
Right.
not work with mid-sense. Yeah.
Mhm.
But so here I have some ratios, and here it will reduce, for example, to 1 octave. Yeah.
Yeah.
So you can see that this ratio change. Yeah. Uh, this is important because the second inlet worked in a different way. It worked with the harmonic series. So it will take the difference between the first inlet, the first harmonic of the harmonic series and the second in this case. So in the first harmonic in the second, we have an octave. Then it will reduce all the range for 1 octave. Yeah.
Yeah.
If we put here on 4, it will reduce all the ratios, in 2 octaves, because between the first harmonic and the fourth harmonic, we have 2 octaves. Yeah. So if you put here a 3, it will be work 2. It will reduce the range of the first harmonic until the third harmonic, but it will distort your pitches because you are not working with octaves reduction. You are working here with 50
Fifth.
reduction, 50 plus 1 octave.
Yeah.
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 So here we have this. We can see that the C sharp here become a F sharp because it would work with 50 plus octave down. Yeah,
Mhm.
but 2 down. It works too with ratios, no, ratios not, but list of, or list of lists. So here we have the diamond tonality of Partch. And here we have the reduction of the octaves. Yeah. I will explain the diamond after it. So the next, I like this next object. This is the modulation notes. It worked with a concept that Daniel Huey showed in the thesis, PhD thesis. The name of the thesis is one analysis of the string quartet number 5 of Ben Johnson, I think.
I think you have it listed in your GitHub in the README of the library. You actually have
Yeah.
all this information.
So. Oh, good. Good, very good. But what in the analysis of the quartet number 5 of Ben Johnson, Daniel Huey, he see that it's very important to Ben Johnson work with the common notes between two different tuning systems. So when he will modulate in between one tuning system and other, he will use notes in common to do it, because it will make currents. Yeah, currents.
So he's used. Okay, so he's got. It's kind of like pivot note modulation type of
Yeah,
thing. You know, it's
yeah,
like they have one in common, and it kind of uses that
yeah.
to, for what they have in common.
Yeah. For example, in tonalist music, yeah, in tonal music, we have, for example, on G sharp in Mi major, E major, it will become A flat in A flat major. Yeah.
Yes.
So it is the same kind of thing, but with tuning systems. So this object will work with this idea. Here we have an MOS structure. Yeah. Here you can see that now it work with ratios too. So here I have this idea that he will tell us that the note blah 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 and the note blah blah can be modulated, used to modulate. You can see that these notes are in two different octaves. Yeah.
Yes.
Here we can see that they are very near. It's a difference of 6 cents. Yeah. Or almost 6 cents. And what is the object will tell to us is that this note that is a F plus one quarter tone, yeah,
Yes.
can be modulated with this note. This note is of the MOS tuning system, yes, of the first inlet. So the structure that are connected in the first inlet. And the second note, this is of this structure, of the diamond of Partch structure. So you can see that this note can be used to modulate between two different tuning systems. But you can see that it's very hard to find these notes, yeah? It's not very easy. Then because that I did this object. It worked the same work like modulation notes, but he will tell us if we change the fundamental of the second tuning system. I was thinking like, for example, I am in one tuning system in my music. So in some point, I want to modulate. So in the first tonality or tuning system, I don't want to change it. So I change the second. So he will ever propose some changes of the second structure of tuning, yeah, not the first. The first is never changed. But here, he will tell us if we change this fundamental, how notes we have in common. So in the first inlet, you have the first is tuning system, the second tuning system. Here we have this third inlet. It's how many cents in difference to the notes can be different to this object, consider it equal, yeah?
Yes.
So here I put some example. Let me copy that. For example, this note on C4 plus 5 cents, yeah?
Yeah.
And a C4 plus 9 cents. These notes, of course, if they are in some tuning system, in this object, this third inlet are configured like 5. The object will consider this note equals, yeah.
Yeah.
But if because they have 4 cents of difference, if we put here 2 cents, he will not we will not see any message because they are not noting common. So here we have this the same in modulation-notes-fund. And here we put what kind of fundamental we want. For example, if we have just a fundamental in the temperate music, yeah, of 12, of with quart tones, with 8 tones, or with 6 tones, or maybe you can choose it. So here we can see a lot of messages. So he will, this is the note of the first tuning system, and this is the note of the second tuning system. And he will claim that the notes will be equal if the difference between the second fundamental will be you change this fundament decreasing 800. Yeah,
Yeah.
you understand it?
I'm sort of, yeah.
Because if I change this fundamental to C4,
Yeah.
these notes
It
will
would
be,
be the
of
same.
course, equal. Yeah. So here we have all the notes that will become equal, but of course with different structure.
Fundamentals.
Yeah. So, yeah. So to
Right.
compare it, we have a second outlet. Yeah.
Yeah.
So here we can see what notes, how many notes we can make if we change some fundamentals. So for example, if we change with this node plus 650, will be two notes in common between this
Right.
structure and this structure. Yeah.
Yes.
I used this function in my piece. Of course, it's not recording yet because of the COVID,
Yeah.
but it works very well, I think. In my compositional things, of course, what I am interested, it works very well. Well, it's not too simple to understand these messages, I think. But what you must to know is that the first note is ever of the first tuning system, and the second note is ever of the second tuning system.
Yeah.
So if we put here, for example, this temperament, of course, we have a lot of notes that will become in common. Yeah. So you can choose some structures. So here we have a very weird fundamental. Yeah. So this is how it works. And of course, so it was just intonation utilities, I think. And now maybe we can see some other things like part diamond. So to construct a part diamond, you need first to know how is the limit. I will write, sorry, my letter is not good. But for example, we have a limit 5. Yeah. What this means is that you will use all the harmonics of the 1 to 5 until 5. But here Partch not work with not odd numbers, just odd numbers. So in the odd numbers to 1 until 5, it's 1, 3, and 5. Yeah.
Yeah.
Okay. Then it is the first thing. It's very simple to do. So if we have here on limit 7, we need to put here 1, 3, 5, and 7. If we put 9, 1, 3, 5, 7, 9. How we in limit 5 we have three harmonics. We need to row 3 diagonals. How it's the name?
Diagonals.
Diagonals. Yeah.
Yeah.
We need 3 diagonals. Yeah. And here, so I need 3 diagonals in this. In this, so to left to right and to right to left. So here I put 3 diagonals. Yeah.
Yeah.
So here in the center of the diamond, we put all this number. So in ratios, so 1 by 1. Here, Partch will put 5 by 5, not 3 by 3, because in the harmonic series 5, it's a E, yeah, and 3, it's a G. So
Yes.
E, it's before G. So here we put a 5 by 5. And here we put a 3 by 3. The first step, it's very simple. You just the how is the name?
Denominator?
Yeah, denominator. We repeat the denominator of this diagonal. So the to the left to right, you repeat the denominator. So sorry, my letter again.
It's
Let
okay.
me change the color maybe to be more beautiful. So and here we put the numerator, yeah.
Yeah.
So sorry,
5.
here is 5.
Yeah.
And here a 3. Yeah. So
Yeah.
here are not our diamond limit 5. So these diagonal are orthogonal diagonal, and these are utonal diagonal. What
Yeah.
this means is that the
It's
maybe let me put
it's the
orthogonal.
yeah. This is
Yeah,
yeah, because
go
I was gonna
ahead.
say these are terms that Harry Partch made
Yeah,
to describe it. So it's like, yeah.
yeah. The orthogonal shorts that are all the diagonal. It's about a set of ratios, not one set, just one set. The orthogonal, it's about one set of ratios. So here we have 3 diagonals of orthogonal shorts. So all the ratios of the left to right is orthogonal shorts, and to right to left is orthogonal shorts. What this means is that orthogonal shorts are using, I will not write this, but are using the harmonic interval of the series, harmonic series in an
Yeah.
ascendant way, so
Yeah.
up, yeah. And the orthogonal are working with a descendant. The same interval of the harmonic series are using in a descendant way. Yeah,
Yeah.
it's not very complex, but
It's
so
like I think of it as like it's the overtone series and the undertone series, really.
yeah, yeah, yeah. It is idea. Yeah. Here we have a limit 5 diamond. So in this outlet, we have all the 3 orthogonal ratios, yeah. So
Yeah.
we can, of course, compare with this. So in the first diagonal, it is, so we have the 1, 1 by 5, 1 by 3, then 5, of course, 1 and 5 by 3, then 3, yeah,
Yeah.
3 by 5 and 1. And here in this outlet, we have the orthogonal shorts. So 1, 5, and 3, 1 by 5, 5 by 5, and 3 by 5. And here 1 by 3, 5 by 3, and 3 by 3. Yeah. These shorts are the same shorts. All these 3 shorts are the same short. Yeah. It's the same tuning, but with different fundamentals. So here the fundamental is, of course, the 1. Here is the 1 by 5, and here is the 1 by 3. So it is the concept, how it works. So we can, of course, in here do diamonds, very big diamonds.
Mm-hmm.
Yeah. And of course, have a thing that it's very important. Harry Partch work with octave reduction. So if we want to see or use the diamond like Harry Partch, you need to put this object here. So he will make these ratios. Yeah. If you compare, oh, sorry. If you compare these ratios to the Genesis of Music book,
Mm-hmm.
you will see that the ratios are the same in the order too. Okay. this is very simple. It's not the complex, but I have
it's a good introduction to kind of the microtonal just intonation world, because
yeah
you're not dealing with crazy numbers and you can
yeah
it's a good start and
good.
to
The second object is the diamond identity. It works at the same in the same way that the diamond, but it works with our identities or our harmonic identities. Yeah. So it will construct all the ratios, but using our identities, because this object work with the concepts of limit. Yeah. So we can just put here one number,
yeah.
not other things. So,
Mhm.
and here we can work with our, so for example, I want to build a diamond with the 11 harmonic and the 31 and the 997, for example. So I like this, I will compose with this. So it is, yeah. And the second one, the last object is the inverse short. It's chord-inverse. So it worked with the let me explain. He will build a new short. So here we have a utonal short, yeah, and it will construct a utonal short. Sorry, here we have a
Yeah.
utonal,
Yeah.
and here we have a utonal short. So what it are doing was doing is that he just invert the intervals, yeah. So these
Right.
two short are
Yes.
symmetrical, identical, yeah.
Yeah.
One go to us to
Ascending.
up,
Yeah.
yeah. Other go to
Right.
down, yeah.
Yes. Yes.
So
Yes.
it's
Yes.
we can see, of course, if we. So here we have this short, yeah,
Yeah.
without the octave reduction. And here we have this short. Oh, of course, sorry.
Because it's
I need this.
yeah.
So
Yeah.
you can see that they are inversal, yeah. It's and it is. This is the function that I implement by using the theory of Partch, of course.
Mhm.
So now we have the interval superposition. This is an important object for me because it will work with the construction of spectral models to change timbres of the SG files. Yeah.
Right.
So here we have three objects of the library OM-Sieves that are part of my MA2. I work with put together the sieves of Shinax and the just intonation. So here we have some objects.
Could you just explain the sort of the sieve function and sort of what it's doing?
Oh yeah.
Just quickly. I don't know if you could do sort of a quick, just to kind of
Yeah, I don't know if
understand.
I can explain it in a better way in English, but it's just Shinax use one start point, so a number, of course, and he will plus with notes. I am not sure if I can. For example, if I have a sieve that is start with the number 3, and we have the unity of 5, for example.
Yeah.
Then we have the 3 plus 5, that is 8, 8 plus 5, that is 13, yeah.
Yeah.
Yeah. 13 plus 5, that is 18 again. Yeah, and so on.
Right.
So that is the theory of sieves. So you can put two sieves together with the sieve union, or do the intersection of sieves that are using numbers that are common in two sieves. It's just that it's very simple,
Mhm.
but it works in a very good way. I don't know why. I like it. So here I have a sieve. Oh yeah, this is important. Here we have, for example, we echachos that are writing, yeah, resertion of Sieves. Echachos spelling. I don't know if this way. Oh, sorry. This guy, sorry, Dmitry Echachos. He will divide the theory of sieves between sieves that are symmetrical and sieves that are not symmetrical. The symmetrical sieves are the palindromy sieves, yeah? So this object build it. For example, here we have a sieve and here we have a very big sieve and a symmetrical sieve. If we put here, we can see that it is palindromy, yeah? So
Yeah.
I have 11, 11, 8, 8, 3, 3, blah, blah, blah. You understand that?
Yeah.
So with this idea, I can construct spectral music with a symmetrical spectrum,
Series.
yeah?
Yeah.
Symmetrical spectrum, yeah. So this interval, this object will construct a symmetrical spectrum in just intonation things. So I have the big,
Yeah.
very big ratios, yeah. Here I have, so for example, here, if I put this out,
Yeah.
of course.
It's gonna.
Oh yeah, this is a very, let me use another interval. So here you can see a very big spectrum. If we put here the same object, we will see that the spectrum is palindromy too. Yeah.
Yeah.
So it is the idea of this object, the interval superposition. And this is important too. Here we have the utonal superposition, or what this means is that the superposition occurs in a descendant way.
Yeah.
And here I have the otonal superposition. Johnson was student with Partch, yeah. He was working with
Yes.
Partch. So he used some concepts that are in common with Partch. The otonal concept are one of this. So here we have then again the utonal shorts, and here we have the, sorry, here I have the otonal shorts and here utonal shorts. Yeah, you can see that
Negative.
it's, yeah, it's again.
Ah.
This is a very big patch, okay? But here I have the structure, yeah. I have a sieve. I have the interval superposition. I change here. I was using this, but I don't need it. But I don't know if it will work. But let's. Yeah, I don't need this here. Oh yeah, I was not using.
It's good to
Sorry.
see other people's patches are just as messy as mine whenever I'm composing.
Yeah. Sorry. So here I have an S-GIF, yes, that I built in Spear, and here I construct, I convert the S-GIF in a list, yeah.
Yeah.
And inside, this is important. You can see that here we have a map area with the function, and here are the functions in the map car.
Right.
Yeah, so here I have 4 functions, but I have a lot of other functions. One is non-processor, and so I do no processor in the SD file. Here I have, I change all the partials of the SD file by the nodes that are in my structure, yeah, my tuning structure. This is an idea of Have some people that are using this. The guy that developed this beer in his PhD thesis talked about it. So it's of course inspired by this idea of construct new new timbres or new samples with change all the partials by tuning systems. Yeah. So here I have tuning systems of Ben Johnson, and here I can see that. Yeah. And of course, it's all our microtonal music. Yeah.
Yeah.
And it will change by the near, what is the near note of this tuning system, and then it will change the notes. Yeah, it's not a very simple patch. Yeah, but in this way that it works. So here I build it. So let me give. So here I have, and then it will make a lot of tests. Yes, test files. These text files will be here. Yeah. And here I have a, let me open this. Yeah, here I have a co-object in the structure is the same that the co-object in the max. Yeah, I have a millisecond number and then the spectrum.
Right. Okay.
That are the index, the frequency, and the amplitude. Yeah, the index, frequency, amplitude. So I use some objects of the, let me see that. For example, if I put here a call, I think I did this. Yeah. I put here a call, three fades is the name of the object, then the sinoids. Yeah. If I read the call in the out files, for example, this, you can hear it.
Yeah.
So what I was thinking is do a lot of texture with this music, this kind of thing. So yeah. So here it's
great.
good. I like.
Yeah, it's really interesting.
Yeah. Yeah, it is. So this is the idea of this object, yeah, that the Johnson interval. He will build some palindrome spectrum in this contest. So, and of course I have others. Let me just here I have the just intonation system of Ben Johnson used in his string quarter number 2 and number 3. All the functions that I create, sorry, I was inspired by the idea of Johnson. That is, in the basically way, it's the superposition or the overlap of the just intervals. Yeah, so it's very simple. Then here we have the start point of Johnson is to divide or be able to see what is the ratio, the media ratio. I don't know what's the mean. Name. Yeah, so I plus 1 for 2, then I divide it by 2 again. Yeah. So it will give me 3 by 2. So I do this again with this result. So I will the answer, the mathematical answer is 5 by 4. So with these 2 intervals, I construct this very big tuning system. Yeah. that Johnstone used. So this is a more musicological, I think, thing, but it's very simple. So it's very simple.
Yeah, and this all these a lot of these patches are in the help patch of the library, so you can
Yeah,
anyone who downloads the library can get all the patches and kind of play about with them.
yeah. The patch of the max that I show before, it is in the site of my university, my master university. It's UFJF. This name I will not
Okay.
spell it. And then CSC patches. So you can,
I'll in the
yeah,
video
here,
description, I'll put a link to
yeah,
this page.
I can send it for you. But I
Perfect.
think I share it with the Facebook group. And of course, if you have some problem, you can write me. This is my email. Yeah. So, and then we have the theory of Evan Wilson. So this theory is divided by the MOS theory and the CPS theory. The MOS, it's very simple. It's Evan Wilson built this theory to construct some microtonal keyboards.
Yeah.
So I have a overlap of just intonation intervals. And then MOS are all the set of ratios that are just two intervals between all the all the sets. Yeah. So here I have this set of ratios. And here with this object, I can verify if this is a MOS or not. Yeah. So this structure is an MOS. So it have the structure of the intervals are S, S, L, S. This is mean that this is the structure, okay, the ratio structure of this set of ratios. This interval, it's I don't know, I forgot the name, sorry. It is small that this interval. So I have S because it's small, of course. Yeah. And this object is larger. So they will use just two objects to construct the MOS. If I put here, oh, this is important. Here I have 11 superpositions because that this number of the 4x3. If I put here, for example, 12, I have this superposition, but this is not a MOS because it have one more interval. So it has 3 intervals in your structure, not just 2. So following the theory of Wilson, this is not considered MOS. Yeah, it's very simple. And mos-check is the idea of find what superposition will be an MOS or no. So here I have all the numbers of superposition that will be an MOS. For example, if I put here 16, I have an MOS.
Right.
But if I put here 15, this is not an MOS because I have more intervals.
Yeah. Okay.
So this is idea. I think that it's related with the tone and semitone of our keyboards. Yeah. So Wilson built the same thing. Yeah.
So can I ask about what articles or books you think, if someone's interested in learning more about Wilson's theory thing, is there anything you have
you can hear
that you think is good?
Yeah, of course. You can read my MA dissertation,
Yeah.
but the to work with the Wilson works is by this woman. It's a very clear book. Yeah. Oh, sorry. I have this is the book.
Right.
Let me put here. Yeah. So this is the name. Yeah. All the theories of every Wilson are inside this book. It's a very good book. It's not simple to understand how the theory of Wilson works, mainly the CPS, the conditions product set, but she explained it very well. So it's not difficult to understand.
That's good.
So here we have in this this object, we have the object that, the interval that we are using to make the overlapping. Here we have how much intervals or how many, I don't know, we are using. And here we have the range. This is important. Here we have a range of 2. This means that is the first harmonic until the 2 harmonic. So if we put 4 here, we have 2 first harmonic at the until the 4D harmonic. Sir, yeah. So we have here 2 octaves, and here I have 1 octave. Here I have 1 octave plus 150. Then it's like the harmonic series. Yeah.
Yeah. So it's just, so you're picking up which point in the harmonic series. Yeah. The first element, second element, third, fourth.
Yeah. For example, if we will work with spectral works or timbre works, yeah, you can use very big range. Yeah. For example,
if you want to write a Murai piece or
yeah. For example, here I have in this, I have on MOS. Oh, sorry. We have this idea. So it's a spectrum. Yeah. It's simple, but it worked very well because it's a homogeneous structure. Yeah, very homogeneous because it has just 2 intervals. Okay, so now we can see this combinations product set theory. This is it's not very easy to explain this theory.
Yeah, I was having a look at these and I was kind of trying to understand what was happening, and I think I needed to read a little bit about Wilson's theory to kind of understand what's going on.
Yeah, theory that are working with geometrical things. Mm-hmm. So the hexany, here the icon of this object is the structure of one eikosany. Yeah. Yeah. Sorry, one hexany. Yeah. Let me. You can see here. Mm-hmm. If I put in the internet. Here I have 2 harmonics. So we have the first, it is a, no, not it's like, yeah, this is an hexany, yeah. Then I have 4 harmonics that I can choose them. The idea of the combinations product set is to combine, of course, the harmonics. So I combine the 4. Here I have 4 letters. Each letter represents 1 harmonic. Yeah. So I have A, B, C, D. So this vertex is about the the harmonics that are the result of the multiplication of the B and the D. So if I have 1, 3, 1, 3, 5, 7, this harmonic will be 3 by 7.
Yes.
Okay. A to 1, B to 3, blah, blah. So this harmonic will be connected with this harmonic because they share the D harmonic in common. So, for example, here they are shared the number 7.
Mm-hmm.
What this mean in musical things? This means that these two harmonics are working in, or they share one same fundamental in the harmonic series. Yeah. So it's not very easy to understand that, but when you see the structure, you understand the structure of the harmonic series, you can see that they are share some harmonic series. So here I have B plus multiplied by D, I have 120U, I think, yeah. 3 by 7, yeah. And here I have a 35. Let me, you understand it?
Yeah.
Yeah. So these two harmonics are share one same fundamental that are not one.
Right.
It's other. It's the, in this case, are the D harmonic series that are 7. So they share a fundamental with the 7, bring with the 7 harmonic. So you can hear this. So this harmonic will be the third harmonic of 7.
Mm-hmm.
Oh, this is tricky part. And this harmonic will be the 5th harmonic of the 7. Yeah.
Right.
So this is the idea of this combinations product set. But how each structure, microtonal structure, are using some numbers of combinations. So in hexany, we have 2 harmonics that are multiplied by themselves.
Yeah.
In the eikosany, we have 3 harmonics that are multiplied by themselves. So this is the structure that we also are talking about. Here we have in this line, we have all the prime numbers of the harmonic series. Yeah.
Yeah.
And here we have another harmonic series that word in the prime numbers. So here I have 1, blah, 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 and here I have 2 by 2 that are the second harmonic, and 2 by 3 that are the third harmonic. You can see that the distance between the 2 and the 3 are the same distance between the 1 and the 3. But it the same, this occur, oh, but yeah. In 5 and 50, this occur again, because we have here an E, yeah, 1 E, and here we have an B. So this is occur in all the harmonic series. So these odd numbers that are not prime numbers, they share fundamental with 2 harmonic series here. For example, 33 is sharing the harmonic series with the 11 and
3.
with 3. Yeah. So this harmonic can be used to construct or build a chord with the 11, yeah, with the fundamental that are 11, that will be 11, and 3 at same time, yeah. And so Narushima have a beautiful phrase that he claims that the combinations product sets open the musical world to the hyperspace world, yeah. So you can work with one chart that have a lot of fundamentals, not just one. And this is, I like this, I like very much. So this is the idea of this object.
Right.
First, he will construct the the vertices, yeah.
Mm-hmm.
So, oh, here. Here I have the vertices of the eikosany theory. And here I have the connections. For example, I get one of these vertices put here in the hexany connection and will tell me what is the harmonics that are connected with this this vertex. So here I have all the ratios that will become ratios with this object, yeah, that are common fundamentals harmonics. You understand it?
Yes, yeah, I from your, yeah, they're shared, but like we were talking about the
Yeah, sure.
13 and
Yes.
yeah.
This is the idea. So it's very simple. So here I have other message, yeah. If you the hexany work with 4 harmonics, not more. So if you put here 5,
Yeah.
yeah, it's not good. This is not the hexany. The CPS or combinations per set hexany needs 4 numbers. For example, blah, 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 blah.
Yeah.
Yeah. This is the idea. Then we have the methodological how everyone Wilson build triads. Yeah, it's not triads like the common music, the traditional music, tonal music. Yeah, but it's the ratios that are shared. Triads that are we are using 3 vertices, not 3 this overlap of thirds. So it's the hexany triads. Here we have, let show here that let me see, just yeah, are working. And here, oh, are 2 concepts. This is, I will not explain. It's very tricky to understand, but he will work with the concepts of sub-harmonic triads and harmonic triads. Are not the same thing that the idea of the otonal and utonal, of course, is a different thing, yeah. Right. But we have this concept of harmonic, sub-harmonic triads and harmonic triads, yeah. Right. The 2 outlets again. So here again, this. Yeah. So in a more fast way, we have the eikosany that are 1 CPS again, but it's a very bigger one. Yeah. Right. So here I have,
it's the same concept, but we're now dealing with like a lot more connections and
yeah. Here we have in hexany we just each vertex have just 2 harmonics. In eikosany we have each vertex have 3 harmonics. Right. So it's this is the difference. So I have this connection it's the same thing, yeah. And here I have the idea of triads. In eikosany we have a lot of triads. I think it's 60 triads, yeah. So here we can can hear that. Someone are, and here the sub-harmonic triads. Oh, sorry. Oh.
Yeah, no, it's there.
Yeah, and so on. Have a lot of things to heard. And here we have in eikosany we have the tetrads. here. Yeah, okay, it finished.